Today I will discuss about dielectric and polarization. Now the question is how different medium responds under electric field. We can classify materials broadly in two categories, one metal and other non-metal. Metal has abundant number of free electrons. So when there is an external electric field, that free electrons arrange themselves. Suppose this is the external field, and if you brought a metallic substance under that field, then what will happen? Negative charge will be accumulated at the surface and positive charge at the opposite surface. Now, inside the metal, the field that is E0, suppose external field be E0, then direction of E0 along this direction and direction of the induced field due to the induced charge. This is the induced charge. Field due to induced charge, that is E internal along this direction. And the magnitude of E0 is equal to E inside. As a result, net field inside is equal to E0 plus E induced, and that is equal to 0. So it is observed that inside a metal there is no field exists. Electric field exists in static condition. Now what will happen in non-metals? Non-metals can be classified non-polarized and polarized. In case of non-polarized material, center of the positive charge and center of the negative charge coincide each other. That is, they exist at the same point, plus and minus. That is called non-polarized. But in case of polarized substance, center of the positive charge inside the atom is not equal to the center of the negative charge. Suppose if we consider the atom of water, then we will see that oxygen has greater ionization potential. So in case of covalent bonding, oxygen attracts the electron pair towards it. As a result, this is hydrogen. So oxygen is partially negative, whereas on the opposite side it is partially positive. This type of material are polarized. So when there is no field exist, this material are polarized. But in case of when there is no external field, these materials are non-polarized. Now what will happen when this non-polarized material come inside a electric field? Suppose this is the direction of the electric field and this is a non-polarized atom, and we know that electrons are attracted against the electric field, external electric field. If we place a free electron, then it will move in this direction. Now in case of non-polarized, we have said that center of the positive and negative coincide each other, but when there is a field, these atoms, electrons move slightly elliptical path. As a result, center of the positive and center of the negative slightly shift from its original position. So this atom under electric field become polarized. So non-polarized material converted into polarized. On the other hand, polarized material, their molecules are polarized, but due to thermal agitation or kinetic energy due to temperature, they are oriented in erratic manner. That means suppose this is negative and positive, in this way. Now, net dipole moment per unit volume is equal to 0, since dipole moment of one atoms nullified by dipole moment of other. But when this type of materials are exposed under electric field, suppose this is the direction of the electric field, dipoles of these materials try to arrange in the direction of the electric field, and that depends on the strength of the electric field. So this becomes negative and positive. So under electric field, they try to rotate themselves in the direction of the external electric field. Now, if we consider a body near to this, there is a inducing body which produces the electric field. Suppose we are considering that type of body to eliminate this. Now, if here there is a positive charge which is the cause of the electric field, so electric field in this direction. Now, this is Q, number of charge at this phase which produce the electric field, and this is the QP charge induced at this phase. This is called QP is induced charge or polarized charge. And Q is the external charge which produce the electric field or induce this material. Now, we know that in case of dipole, this is suppose a dipole, and this is negative and this is positive. So dipole vector P is from negative to positive, direction of the dipole from negative to positive. But if we consider any point at this axial point, then direction of the field due to the pole along this direction from positive to negative. So EP, we can say that direction of EP, that is EP kappa, that is direction is equal to minus P kappa. So always opposite in direction. Now what will happen? This is inducing charge and this is induced charge QP, this is QP and this is Q. Inside the material, external field, that is E0, along this direction from positive to negative, and EP, that is field due to polarize, along this direction. So there is a net field inside which is E is equal to E0 plus EP. Now the polarizing vector, what is that? Polarizing vector. This is the dipole moment per unit volume. Now, if we consider a small volume inside our dielectric medium, suppose this is a dielectric slab, and we're considering a very small portion like this. This volume consists of huge number of molecules. Suppose we are taking the length of this volume as the distance between the positive and negative charge of a dipole. Suppose this is a molecular dipole and here it is a negative and it is a positive. And in case of dipole, we usually take this length as twice L, and if this is Q, then dipole moment is equal to 2QL. Now, for simplicity, we are taking one molecule thickness. Now, if the surface charge density of the polarized charge be sigma P is equal to surface charge density of polarized charge. Therefore, field due to this polarized charge is equal to sigma p divided by epsilon 0. This is a EP polarized field inside this volume, and the dipole moment. So the total number of charge is equal to sigma p into cross section area of this volume is equal to total charge into twice L. That is the total dipole moment. Dipole moment of the volume. Now, what is the volume of this cuboid? That is, volume is equal to twice L, since length is taken as twice L, and cross section area A. Therefore, dipole moment per unit volume or polarization vector, polarization vector P is equal to, its magnitude is equal to sigma P into twice AL divided by twice AL. Cancelled is equal to sigma P. So we can say that polarized charge density is numerically equal to the magnitude of the polarizing vector. So P is equal to sigma P. This is important. Now we know that in case of dipole, suppose this is a dipole, negative, direction of the dipole along this is the direction of the dipole, and direction of the field due to the dipole along this direction, positive to negative. So we can say that direction of the P is opposite to direction of the E, because electric field starts from positive and up to negative. And E is equal to, E polarized is equal to sigma P divided by epsilon 0. Therefore, we can say that EP is equal to minus P by epsilon 0. Now, we know that inside a dielectric slab, there are two fields, one external field, another field due to the polarization. So, the field inside the dielectric medium is equal to vector sum of this E. There is the resultant field inside the dielectric, and magnitude of the resultant field, it is directly proportional to the external field, and we can say that E is equal to E0 by epsilon R. Epsilon R is called relative permittivity. Now, we know that direction of EP is opposite to direction of the E0. So, resultant sum of these two will be actually subtraction of these two. So, E0 minus EP is equal to E. Now, E0 minus EP is equal to, and E is equal to E0 by epsilon R. So, EP is equal to E0 minus E0 by epsilon R. That means EP is equal to E0 into 1 minus 1 by epsilon R. So, polarizing field is equal to external field into 1 minus 1 by E0 R. If we use the vector notation, then EP is equal to minus E0 vector, because direction of EP is opposite to direction of E0, 1 by 1 epsilon R. Okay, the polarizing charge. Suppose this is an inducing body, it has positive charge, so that there is electric field along this direction. This is E0, and due to this that field, the dielectric medium, and this induced charge or polarizing charge, QP. This is Q and this is QP. Now, Q is proportional to QP, and from the previous relation, we can say that from this relation, that is E0 minus EP is equal to E, the resultant. E0, that is sigma of sigma by epsilon 0. This sigma is surface charge density of inducing material, minus sigma P by epsilon 0 is equal to this is called Q sigma free F by epsilon 0. Free, that means the charge of the inducing body, the flux of which is not engaged with the polarizing charge. That is free charge. That is called free charge. So we can say that free charge is the difference between free charge Q free is equal to Q minus Q polarization. Now we can say that sigma is equal to sigma P is equal to sigma F, and this is Q, all have same area, so we can convert easily sigma to Q minus Q polarized is equal to QP. And we know that E is equal to E0 by epsilon R. So we can say that Q free is equal to Q by epsilon R. Q free is equal to Q minus Q polarized is equal to Q by epsilon R. So QP is equal to Q into 1 minus 1 by epsilon R. So same relation as the previous one. EP is equal to E0 into 1 minus 1 by epsilon R, and here QP is equal to Q into 1 minus 1 by epsilon R. Now electric displacement vector. D. We know that E is equal to E0 plus EP, and also we know that E0 EP is equal to minus P by epsilon 0, so minus P by epsilon 0. Therefore epsilon 0 into E vector is equal to epsilon 0 is 0 minus P. Therefore epsilon 0 is 0 is equal to epsilon 0 plus P. This is called displacement vector. This is very important because we can apply Gauss's theorem in dielectric medium using this displacement vector. According to Gauss's theorem, E dot ds is equal to Q in by epsilon 0. So we can write it as E epsilon 0 into E ds is equal to Q in. So if we apply Gauss's theorem inside dielectric, then that will be epsilon 0 E plus P ds is equal to Q in. Clear? This Q in is called Q free. Now what will happen when we increase the electric field intensity? Suppose this is a dielectric medium, and under the electric field, negative and positive are polarized inside the. Now if we increase the intensity of the electric field, if we increase this intensity gradually, then a time will come when this bounded electron, this is called bounded electron, this electron or polarized electron, atom cannot hold this electron and they will jump from the atom, and this electron become a free electron. That electron behaves like a free electron. When it travels through the air molecules, we know that when an electron with high velocity or any have some kinetic energy, when it settles on orbit of another atom, then it emits some light, electromagnetic wave, and we will get the spark. That is called corona-discharge. And the field after which this electron comes out from the atom is called breakdown field. And the corresponding voltage is called breakdown voltage. Now, we know that when a body is being charged, suppose there is a body, considering a metallic body, it is being charged with some positive. Since it is a metallic body, outer surface of the body should be equipotential. So every point on every point of the metallic body have constant potential. Now, considering a sphere, suppose this is a sphere having charge q plus q, therefore surface charge density is equal to q by 4 pi r square, that is equal to sigma. Now field at the surface, electric field E is equal to sigma by epsilon 0, and potential V is equal to q by 4 pi epsilon 0 into r. Now we can say that V by r is equal to q by 4 pi r square into epsilon 0, that is sigma by epsilon 0 is equal to E. Now we can say that if potential V is constant, if V is constant, then E proportional to 1 by r, and sigma, also sigma proportional to 1 by r. Therefore, we can say that in case of equipotential surface, the radius of curvature of the surface is different at different places. Suppose here the radius of curvature is small and this is inward. This is comparatively flattened surface, so its radius of curvature is greater. So we can say that charge density at every point of the surface is not constant, except it is a sphere. For any other surfaces, surface charge density is not equal. That depends on the curvature of the surface at a different portion. So smaller the radius of curvature, greater will be the field. Therefore, we can say that field at this point is greater than field at this point. This is more denser. That is why we usually use sharp end for thunderbolt arrestor, that is lightning arrestor, lightning conductor. In case of lightning conductor, the top of the lightning conductor is made sharp due to this. And when a body have a certain potential V, potential is equal at every point of this body, but radius of curvature is very small at this portion. So the field at this portion is very, very high. As a result, the surrounding medium, that is air, they are exposed under this field, and we know that the field, breakdown field for air is equal to 3 into 10 to the power 6 volt per meter. So when it go beyond 3 into 10 to the power 6 volt per meter, then corona-discharge takes place, that is electron from the air will jump towards the body if it is positive.